Welcome to Lecture 5 Reinforcement Learning. This is your Professor Atif Reed Muhammad. This is a sequence of lectures at University of the Cumberlands at Kentucky, PhD AI 830. So, this lecture covers how machines can learn to make good decisions by interacting with their environment. Reinforcement learning is one of the most exciting areas of artificial intelligence because it allows computers to learn from experience just like humans do. Reinforcement learning is used in many real-world applications today. Self-driving cars use it to learn safe driving behavior. Video game playing systems like AlphaGo use it to master complex games. Robots use it to learn how to pick up objects and move around. Throughout this lecture, we'll learn the key ideas, algorithms, and applications of reinforcement learning. Imagine teaching a dog to sit. When the dog sits, you give it a treat. Over time, the dog learns that sitting leads to rewards, so it sits more often. This is the basic idea of reinforcement learning. Learn actions that lead to rewards. The outline shows here that we will cover in this lecture. First, we'll learn the basic concepts of definitions of reinforcement learning. We'll understand what rewards are, how agents learn from them, and why this approach works for many problems. We'll also study the passive reinforcement learning, where an agent watches and learns without making decisions. Then we move to active reinforcement learning, where the agent makes choices and learns from the results. We'll study Q-learning, which is one of the most important algorithms in this field. We will see the real-world applications of reinforcement learning. In this lecture, we'll build up from simple ideas to complex ones. By the end, you will understand how computers learn to play games better than humans and how they control robots in the real world. So, welcome to the part 1 of this lecture. This section covers the fundamental ideas behind reinforcement learning. You need to understand these basic concepts before moving to the more advanced algorithms later in the lecture. Reinforcement learning is different from other types of learning. In supervised learning, we have correct answers to teach from. In reinforcement learning, we only get rewards or punishments. This makes the problem harder but also more flexible and powerful. Consider a robot learning to walk. Nobody tells it your left foot is at the wrong angle. Instead, when it falls, it loses points. When it moves forward smoothly, it gains points. Over time, it learns which movements lead to success. Reinforcement learning means learning through interaction. An agent takes actions in an environment. The environment gives the agent rewards or penalties based on its actions. The agent learns which actions lead to better rewards. The process is like exploring a new era, and you try different paths and remember which ones have good views or restaurants. Let's say if you're going in a new area to find out the restaurants, you do not need anyone to teach you where to go. You learn by exploring and keeping track of what you find. A machine learning program that plays chess learns by playing many games. When it wins, it gets a positive reward. When it loses, it gets a negative reward. Over thousands of games, it learns which moves are good and which are bad. The main goal of reinforcement learning is to get as much total reward as possible. This is not just about getting one good reward right now. It is about getting good rewards over the long time. Sometime you need to accept a small reward now to get a much bigger reward later. This is different from being greedy. A greedy strategy always picks the best immediate choice, but reinforcement learning learns that sometime you need to wait or take a small loss to get a bigger gain later. This is why reinforcement learning can achieve intelligent behavior. A student studies hard for an exam instead of playing video games today. The student gets less fun today but gains much better test scores and future job opportunities. The cumulative reward of studying is higher even though immediate reward is lower. Rewards can come right away or much later. As immediate reward is feedback you get right after an action. A delayed reward comes fast after many steps. For example, a chess player gets feedback only when the game ends, not after each move. The credit assignment problem asks which of my past actions actually caused this reward. If you make 20 moves in a game and then win, which moves were important? This is hard to figure out. Did one move matter or did many moves matter together? In Pac Man, you get points immediately when you eat a pellet, but you lose the game only much later if you hit a ghost. Your system must learn that avoiding ghosts now leads to surviving later, even though you do not see a reward for the several moves. So I ask you a question. In your real life, what reward structure you have studied? Now that's an area that I would suggest you to conduct a study in depth using Google Scholar or IEEE Explore to figure out that how a reward structure has been given in the research that has been published over last decade or so since the generative pre-trained transformers started in 2016 2017 and now we are in 2026. And so I would suggest to you, whenever you're listening to this lecture or watching this lecture, you must conduct a study to establish the idea of the reward structure, which the researchers or authors have shared the utilization of immediate rewards, delayed rewards, or credit assignment problem. So that'll give you a better understanding in that case. Now let's look into cumulative reward or return. The return is the total of all future rewards from now on. If you make a good decision now, you want to know how much total reward that leads to in the future. This includes rewards you get immediately and rewards you get later. We discount future rewards because we care more about rewards we get soon. A reward today is worth more than the same reward next year. We multiply each future reward by a discount factor which is less than 1. So that's gamma is less than 1. Rewards far in the future gets multiplied by the gamma many times and become very small. Suppose you can make 2 investments. Investment A gives you $100 in 1 year. Investment B gives you $50 today and $60 in 1 year. With a discount factor of 0.9, investment A returns 100 times 0.9 equals to $90 today. Investment B returns 50 plus 60 times 0.9 equals $104 today. So investment B is better in that case. Alright, now let's look into the passive reinforcement learning. We learn about passive reinforcement learning on the basis of the reinforcement learning that we have started in this lecture. Passive means the agent does not make choices about what to do. The agent watches what happens and learns from the results. Someone or something else decides the actions. Passive learning is useful when you cannot control what happens but can learn from observation. A doctor learns by watching other doctors work. A trader learns by studying past market data. Neither the doctor nor the trader creates the situations. They just learn from what they observe. Imagine a robot that watches humans work in a factory but does not perform any actions itself. The robot observes which actions lead to successful products and which lead to errors. Later, when the robot takes over, it uses what it learned. Direct utility estimation is the simplest way to learn from observation. The idea is very straightforward. Each time you visit a state, note what total reward you get from that point onward. Average will the reward you get starting from that state. That average is your estimate of the value of the state. This method is easy to understand and implement. You do not need to model how the world works. You just collect data and calculate averages. However, it needs a lot of data to get good average. You must visit each state many times. If there are millions of states, this takes forever. You keep the food diary and record your energy level 1 hour after eating each meal. If you eat pizza 50 times and record your energy each time, the average energy after pizza is your estimate of how much energy pizza provides. If you eat it only once, your estimate is based on just one example and is unreliable. Adaptive dynamic programming is more efficient than direct utility estimation. Instead of just averaging rewards, you build a model of how the world works. You learn which states you can reach from each state and which with what probability. Then you use dynamic programming to calculate the value of each state. This approach is better because you can learn from limited data. If you see a transition once, you can use it. You combine your experience with a model of the world. This lets you learn faster. However, building a model takes work and requires learning the transition probabilities. A weather forecaster learns that when it is cloudy in the morning, there is a 70% chance of rain in the afternoon and 30% chance of the sun. Rather than waiting for the afternoon many times, the forecaster can immediately predict what usually happens next. This model helps make better predictions faster. Temporal difference learning. Temporal difference learning combines the best parts of direct utility estimation and adaptive DP, and that's the difference. The TD learning combines in terms of updating your value estimates by looking at the difference between what you predicted and what actually happened. This error tells you to adjust your progress and in terms of guessing. TD or temporal difference learning also uses bootstrapping. This means you use your current estimate of the next state to update the current state. You do not need to wait until the end of the episode to update. You update after each step based on your current predictions. This makes learning fast. Alright, what's next? TD update rule. This formula is the core of temporal difference learning. Let me break it down step by step. You have a current state, VFS, of how good it is to be in the state S. You take an action and get reward R. You move to state S prime. You look at your estimate of that new state Vs prime. The error term is R plus, and this tells you whether your old prediction was too high or too low. If the error is positive, your old estimate was too low. So you estimate that studying for 2 hours leads to a test score of 80. You study for 2 hours and score 85. Your error is 85 minus 80 equals 5. If your learning rate is 0.1, you increase your estimate by 0.1 times 5 equals 0.5. Your new estimate becomes 80.5. Next time you study for 2 hours, you expect a score closer to 85. Active reinforcement learning. Active reinforcement learning means the agent makes choices about which actions to take. The agent learns through trial and error. It must decide whether to try new things or use what it already knows. Active learning is harder than passive learning because now the agent must explore wisely. If it only tries new things, it wastes time on bad actions. If it only uses what it knows, it misses better actions. This balance is called the exploration exploitation trade off. A restaurant customer can either order the same dish they like or try something new on the menu. If they always order the same dish, they miss out on even better food. If they always try new things, they waste money on bad meals. A smart customer balances exploring new dishes with enjoying favorites. Exploration means trying actions you have not tried much or do not know about. You risk getting bad rewards, but you might discover great new actions. Exploration is how you learn new things and improve your understanding. Exploration also means using the actions you already know are good. You get reliable rewards and avoid mistakes. But if you only exploit, you never discover better actions. The challenge is to balance these two needs. A job hunter can apply for similar jobs they are qualified for right now, or they can learn new skills that open up better opportunities later. Applying for known jobs is exploitation. Learning new skills is exploration. Both matter to find the best long term position. Now let's look at exploration strategies. Different strategies help you balance exploration and exploitation. Epsilon greedy is simple. Most of the time, you pick the action that looks best, but with small probability epsilon, you pick a random action. This guarantees you keep exploring a little bit. Upper confidence bound is smarter. For each action. You estimate not just the average reward but also your uncertainty. You feel more confident about actions you have tried many times. You feel uncertain about actions you tried few times. You pick actions that look promising, either because they have high average reward or because you are uncertain and might learn something big. Epsilon greedy is like a student who usually studies for the hardest class but once in a while studies for a different class just to see if it is harder than they thought. UCB is like picking classes based on both your current grade and how much you stand to improve. Now let's look at safe exploration. Safe exploration means exploring new actions while avoiding dangerous situations. In robotics, a robot must learn to move faster but must never drop what it is holding. In autonomous driving, a car must learn better driving but must never crash. The way to do this is to add constraints. You tell the learning system you can try anything you want, but these things must never happen. The system learns within those boundaries. This is harder than unconstrained learning, but It is essential when real harm can happen. A medical system learns new treatments while using constraints like never give a dose that would cause organ damage, never use drugs known to interact badly. The system explores treatments within these safety bounds. This lets doctors benefit from learning systems without risking patients. Now let's jump into learn Q learning. So Q learning is one of the most important algorithms in reinforcement learning. Instead of learning the value of a state, you learn the value of taking a specific action in a state. This is called QSFA. The Q means quality of taking actions A in the state S. Q learning is off policy. This means you can learn the best policy while actually following a different exploratory policy. While you explore randomly, you learn what the best strategy would be. This separation makes Q learning very powerful. A student takes practice tests to learn what strategies work best. The student uses a new strategy on each practice test, exploring what works. At the same time, the student is learning which strategy performs best on test day. When the actual test comes, the student uses the best strategy they discovered. So this is the Q learning update rule. It is very similar to TD learning, temporal difference, but with an important difference. Instead of using your prediction of the next state, you use the maximum Q value possible in the next state. The max term means you assume that from the next state you will pick the best possible action. You update your current action based on the best you could possibly do next. This guides learning toward the optimal policy. A chess player makes a move and wonders, was this a good move? That player evaluates it based on the best response the player could make next turn, not what the player actually plans to do. If the player can make a brilliant move next turn, then this current move looks good even if it seems risky. The Q learning algorithm does the same thing. Now let's look at function approximation. In small problems, you can store Q values in a table. For each state action pair, you have one number. But in large problems, there are too many states. A video game has millions of possible screens. You cannot store a table with millions of entries. Instead, you use function approximation. You learn a function that takes a state as input and outputs Q values. Neural networks are perfect for this. A neural network learns to estimate Q values for new states based on patterns it learned from old states. A human learns to recognize dogs after seeing 30 dogs. You can recognize a new dog you have never seen. You do not remember all 30 dogs. You learn patterns like pointy ears for legs, fluffy tail. A neural network does the same thing, learning patterns that generalize. Now let's look into deep reinforcement learning. Deep reinforcement learning puts together neural networks and Q learning. The neural network learns a Q function that takes states and outputs Q values. The RL algorithm trains the network to make good predictions. Deep RL or deep reinforcement learning can handle very complex problems. It works with pixel images as input. It can learn policies for robots that have many joints and sensors. This combination of deep learning and reinforcement learning has led to breakthroughs through results in games and robotics. A system learns to play Atari video games by looking at the raw pixels on the screen, just like a human sees it. The neural network learns that certain pixel patterns mean the player is about to hit an obstacle. over millions of games. It learns that this means avoid this direction. Eventually, it plays better than any human. Reinforcement learning is used in many important applications today. In games, reinforcement learning systems have beaten world champions in chess, Go, and StarCraft. These systems learn strategies that surprised expert players. In robotics, reinforcement learning teaches robots to pick up objects, walk, and run. In autonomous vehicles, reinforcement learning helps cars learn to drive safely and efficiently. In power systems, reinforcement learning optimizes how electricity is distributed. In recommendation systems, reinforcement learning learns which content each user will enjoy. Netflix uses reinforcement learning to decide which shows to recommend. The system tries different recommendations and learns which ones get watched. A user who watches science fiction gets recommendation based on past viewing patterns combined with learning what similar users like. This lecture covered the key ideas of reinforcement learning. You learned the reinforcement learning is learning through interaction. An agent takes actions, gets rewards, and learns which learning and cue learning, which is learning and which is cue learning. The actions are good, bad, the reward or penalty. You learn different algorithms for learning, direct utility, a temporal difference learning, and cue learning. The main challenges in reinforcement learning are balancing exploration and exploitation. You must try to new things to find better solutions, but also use what you know works. Deep reinforcement learning extends these ideas to complex problems using neural networks. Imagine a company wants to use reinforcement learning to improve customer service. The system learns which responses customers like, and it explores different responses while also using strategies that work. After months of learning, the system handles customer requests better than any single human agent. The company benefits from continued learning and improvement over time. See you in the next lecture.